Hello dear viewers, guess who's back? In this video we're gonna do some magic. We'll take a couple of advanced problems in magnetostatics and turn them into rather simple problems in electrostatics. So, let's begin. The title of this video is Solenoids and Poloids. So let us first define what do we mean by these terms. What is a solenoid? You can think of a solenoid as an infinite cylinder of arbitrary cross-section. To generate a solenoid, pick a planar curve and translate it along the perpendicular axis. So this is the curve. We shall call this curve C. It defines a cross-section, and that cross-section shall be translated along the z-axis. In this way, we get something which we shall call the solenoid. We will allow this solenoid to carry current. We shall look at the current, the surface current K, which wraps around the solenoid. This is the constant surface current, and it wraps the solenoid around in a tangential manner. With this configuration, we will try to calculate its magnetic field. To do that, let us first analyze what is the current density of such a solenoid. We will focus on one slice of one cross-section of the solenoid, which looks something like this. Now the curve C can be parametrized by a function f. So all the points on the curve C will be given by the formula f of x and y is equal to 0. So we can always choose an f to satisfy this, although f is definitely not unique. We shall choose an f such that inside the solenoid, this is the region we shall denote by s, inside the solenoid this function is positive, and outside the solenoid this function is negative. This is very convenient because now we can introduce something which we shall call the indicator function. The indicator function is just the Heaviside theta function applied to the function f. Now if you remember, the Heaviside theta function, if you plug in a positive argument, it spits out 1, and if you plug in the negative argument, it spits out 0. So inside the solenoid, where f is positive, the indicator function will give us 1, and outside the solenoid, where the indicator function is negative, the theta function spits out 0. That's why we call it the indicator function. It indicates whether we are located inside the solenoid or outside the solenoid. And this function is very convenient in calculation of this current density. Now why is that? If we take the gradient of such a function, we notice that it vanishes almost everywhere, right? Because the function is constant both outside and inside the solenoid, so its gradient vanishes there. And the only place where the gradient is non-zero is exactly on the curve C, where the function jumps from the value 0 outside of the solenoid to the value 1 inside the solenoid. So this is a sharp jump, and it happens only on the curve C, and a natural way to describe such a jump is a Dirac delta function. So the gradient of the indicator function is proportional to the delta function, and this gradient points along the normal to the curve pointing inside the solenoid. So this is this normal n. On the other hand, the surface or the current density of a solenoid is proportional to the surface current K introduced in the last slide. It's pointing along the tangent of the curve, and it's present only on the curve C. So the surface current flows only on the boundary of the solenoid. This is described by the curve C, and points along the vector t to the tangent. Now it's easy to see that we can exchange both the delta function here and the tangent vector here. We can write all of this in terms of the gradient of the indicator function. Now the gradient points along the normal, but the current points along the tangent, so we have to introduce another cross product. If we take the cross product of the gradient with the z hat, which is the unit vector perpendicular to this plane, which means that it's pointing directly at you, my dear viewer, we get the formula for the current density of the solenoid in terms of the gradient of the indicator function. Now, why is this particularly convenient? Well, because since z hat and k are constant, we can write the surface, the current density, in terms of a curl of some vector. So J in the solenoid case can be written as a curl of some vector field. Now, usually when you have a current density written as a curl of some vector, such vectors are called magnetization. So here we have an effective magnetization corresponding to our solenoid. And this magnetization is proportional to the surface current K, to the indicator function, and pointing along the z-axis. So what does this mean? This means that the effective magnetization for this problem is constant everywhere inside the solenoid, where the indicator function equals 1, has the magnitude of the surface current, and points along the z-axis. One other very important thing for this magnetization is that its divergence vanishes. This is not too difficult to see because the magnetization points along the z-axis, but it has no z dependence here, so its divergence almost trivially vanishes. Okay, great. So this was the analysis for the case of a solenoid. Now let us take a look at the other problem. What is a poloid? Well, poloid, as you can see, is this beautiful butterfly. It is constructed in a similar manner to that of the solenoid. So we take an arbitrary cross-section, a planar cross-section, and instead of translating it along the perpendicular axis, now we rotate it about an axis lying in that plane. Okay, and that way we get a surface of revolution of constant cross-section. Now, such a surface of revolution in general will look like a torus, a deformed torus of constant cross-section. The name poloid comes from the sense in which the current flows around such a torus. A poloid direction is exactly what you would get if you have current in each cross-section flowing in this way, and when you represent this as a direction on the surface of revolution, such a direction is called a poloid direction. Okay, so now let us now proceed with the analysis for the current density in this case. We introduce the coordinate system. Now the z-axis is the axis around which we do the rotation, and the perpendicular axis to that is the radial axis, which we shall denote by S as an homage to our dear Professor Griffiths. Here we have to be careful because there are some subtleties not present in the solenoid case. First of all, you may see that this cross-section I've drawn here has a part of which is tangent to the z-axis. So if you think of rotating this cross-section, you would not get a torus, you would get a deformed torus which doesn't have a hole inside it. But this is also an admissible cross-section, so let us do a generalized analysis where we have both the regular, let's say, part and this part which is tangential to the z-axis. Now, when you have this part, let us focus first on this part, which is flows along the z-axis. When you rotate something which is on the z-axis, when you rotate along the z-axis, you don't get a surface of revolution. So any current flowing around this area will remain linear current, right? It will remain on the z-axis. And for the rest of this poloid, which is not on the z-axis, when rotated, it would really generate a surface of revolution, and we will have a contribution from the surface current. So there are two contributions to be taken care of. Well, first one, the linear current along the z-axis. We have a total current I. Now remember, in the case of the solenoid, our solenoid was infinite and we introduced the surface current. Now our poloid is finite, and therefore we can calculate with the total current I. And this current I, for this linear part lying on the z-axis, can be written down in this way. So the linear current is proportional to the total current. It's pointing along the z-axis. It is located on the z-axis, so the location of this current is described by the delta function of the radial vector s. So this current is present only where s is equal to 0, which is exactly the z-axis. And of course, we have to be careful that we have this contribution only inside of this solenoid. This poloid. So we introduce the indicator function theta of s, where this s is now the cross section of the poloid. So these three terms define where the linear current is located and where it is pointing at. For the surface current obtained by taking a surface of revolution of this part, we can do a similar analysis to that of a solenoid case. So if we introduce the curve C, which describes the boundary of this poloid, we represent it by the function f equals 0, introduce the inside of the poloid, outside of the poloid, and we introduce the indicator function as well. It's not too difficult to see that we can use the analysis as in the solenoid case to write the surface current in the exactly same manner. So the surface current times the gradient of the indicator function and a cross product with phi hat, where phi hat is now the unit vector pointing perpendicularly to this surface, which again means directly at you, my dear viewer. Note that there's a technical subtlety here. We had to introduce the theta function of the radial variable s to note that this is really a surface current contribution. So in here there is no part of the current which flows along the z-axis. So this is sort of like a safety measure, because if you think about it, the phi hat vector can only be defined for points off the z-axis. Okay, and there's still another subtlety to be considered here. You see this surface current K is no longer constant as it was in the case of a solenoid, but now it is given by this expression. So K is equal to I divided by 2 pi s, where s is the distance from the z-axis. And how to explain such a formula? Well, if you take a look at exactly this point of the cross section and you rotate it around the z-axis, you would get a circle, right? A circle of circumference 2 pi s. So the total current I, which gets to this point, is distributed along this circle. Therefore, the surface current density is the total current divided by the length of this curve, the length of this circle, which is 2 pi s. Therefore, K is equal to I over 2 pi s in here. And when you plug this value of k into this formula, and you do a bit of simplification on these two terms, you can find again that the current density for the poloid case indeed can be written again as a curl of some vector field. And by now we know that when this is the case, we can define the effective magnetization of the poloid with this expression inside of these brackets. So magnetization for a poloid case is proportional to the total current I flowing in the poloid, proportional to the indicator function, meaning that it is present only inside the poloid while it vanishes outside the poloid. It points along the phi hat direction, so it wraps around the z-axis and is inversely proportional to the distance from the axis. Again, there's this factor, theta function of s, which you can think of as securing that both 1 over s and phi hat have well-defined meanings. There's an additional similarity to the magnetization of the solenoid in that the divergence of the magnetization for the poloid case also vanishes. Again, since the magnetization is pointing along the phi hat direction and nothing here depends on the variable phi, it's easy to see that the divergence will vanish. Okay, great. So we have two examples in which we have been able to express the current density in terms of a curl of a magnetization. So let us see what does that imply in our Maxwell equations for magnetostatics. Now you remember the basic equations for magnetostatics are these two: the vanishing of the divergence of the magnetic field and the curl of the magnetic field being proportional to the current. Now, since in magnetostatics the divergence of the current is zero, we can always write J as a curl of M for some M, and we have been able to do so explicitly in these two cases. Now, if we plug in this magnetization in the Maxwell equations, we get, for the second Maxwell equation, we can rearrange the second Maxwell equation to get the curl of some vector vanishing. So if we introduce the auxiliary vector h being defined as b divided by mu naught minus m, its curl vanishes. So the second Maxwell equation says that the curl of h vanishes. On the other hand, for the first Maxwell equation, if we exchange b for h and m, we get that the divergence of h is equal to the minus divergence of m. So if you write it one by the other, you see that this field h satisfies basically the equations of electrostatics, right? If you exchange the electric field for the auxiliary field h and the charge density for the divergence of the magnetization, you basically get the equations of electrostatics. And we know what the solution to equations of electrostatics is. This is very simple, just the Coulomb law. In our case, the divergence of the magnetization vanishes. This is as if in electrostatics the charge density would vanish. And if the fields vanish in infinity, then the solution is trivial. The electric field vanishes, or in our case, the H field vanishes. But if the H field vanishes, then the magnetic field is just mu naught times the magnetization. Pretty cool, right? So for our solenoid case, we get that the magnetic field of a solenoid is equal to mu naught times the surface current K times the indicator function and pointing along the z-axis. So inside the solenoid, the field is uniform with the magnitude mu naught K, and pointing along the axis of the solenoid. Outside the solenoid, it vanishes. As for the poloid, the magnetic field is this. It's mu naught I divided by 2 pi s, and inside the solenoid, it is given by this expression. Outside the solenoid, it vanishes, and it wraps around the z-axis, pointing in the phi hat direction. Now, if you look closely, the magnetic field of the poloid case is exactly the same as of the straight linear current. So what do you think? Is this coincidence or not? Let me know what you think in the comments. And with this, we finish the video for today. Thank you for watching. You can follow me on these various social platforms. Until next time, stay sharp, keep solving, and keep evolving.